the next, just very briefly, I just want to mention something before we get, like, in the future lectures, we'll kind of talk about how we control muscle tension, right? And we'll talk about the types of and amount of muscle fibers that are activated, right? Over here, we'll talk a little bit about the frequency of stimulation, neuron stimulation in that, and how you control muscle tension and strength of contraction and muscle tone through those, right? So we're talking about that, all leading to contractile force. And then I just want to do a brief thing on the on this concept of the length tension relationship. That is, there's a certain ideal length of the entire muscle and consequently the sarcomere, where muscle contraction, where you get the most tensile force, tension force generated. Okay, and that's going to happen at a gross anatomy scale as well as at the sarcomere level. We'll talk about it at the sarcomere level here, right? This length and tension relationship here. So here's from a workout, some kind of workout guide, right? And they're telling you, all right, do this movement right here. You're going to lower the weight over here very slowly, right? Your muscle is going to stretch out during this. Then you're going to hold it for a minute. Here's going to be some tension generated because you're holding this weight over here, right? Your muscles at a certain levels of stretchness, right? And then you're going to move back way where your muscle is going to contract, right? Shorten and create a pulling force here actively, right? It's going to move and something's going to move. And then they're telling you, all right, hold it for a couple seconds there. Tension is going to still be generated, right? But you're not causing any movement right there. Right? What you want to notice here is the length of muscle. And they do these kind of things because there's optimal lengths of muscle contraction where you can get the most force and therefore kind of get the best workout. And this is kind of at a gross level over here. And by gross, I mean just gross anatomy, right? So when you see a muscle shorten its length, right, from this muscle length from here to over here is going to shorten from here to here, right? It's going to bulge up in the middle. And when it does so, it's going to create that pulling force, right? What that means, there's going to be a corresponding decrease in all the sarcomeres of there, because that's what's causing it to shorten. All right, so you're going from this length to this length. So that's how you get muscle shortening over here on any given contraction length, right? So your overall muscle length is always going to be due to this overall sarcomere length, right? There's a direct correspondence. So the idea here, one of the properties of the muscle is that we can contract it at a range of different lengths, right? There's going to be a certain amount of overlap between the myosin heads and the actin filaments, and there can be a contraction over various lengths of that, over various amounts of overlap, right? Some of them are going to be optimal, some are going to be less than optimal. And what we'll see is that it's going to be due to the amount of overlap, basically. Okay, so first, I just want to take a moment here also about something about reading graphs. Right? So when you look at graphs like this will be very important as we get into the nervous system and a little bit later on when we talk about muscle tension in greater detail. But I want to mention this right now, right? What this graph is showing here is that there is an electrical impulse going down the muscle cell, and then there's electrical impulse, down the neuron, then down the muscle cell. And then there's some tension generated because of that, right? So what you're looking at here is time, right? Here's time. Here's time 0. Over here, they took a measurement, right? They stuck an electrode in here, measured the membrane potential over there, and they found it's -70. So they put a little dot here. And they took it at time 1. And they put a dot here, and they said, oh, it's still -70. Then they took it at time 2, and they're like, oh my God, look where it is. It's +30, right? It went from -70 to +30 at this point. And then they looked at it at, say, time 3, and they said, oh, it's about, 0 over here or something, right? Whatever. And then they looked at it time 4, They said it was about minus 70 again. They looked at it time 5. Oh, it looked dipped below minus 70. It was minus 80. Right, so they're measuring it at these different time points over there, very kind of in very, very small increments, right? This is like 2 milliseconds over here from time 2 to time 4 or whatever. Right? Does everybody understand that they're measuring the membrane potential at any given point for this brief second where this action potential is traveling down the nerve right here? And in this one, they're looking, at the same kind of time scale at the muscle fiber, right? This signal going down it, and they find it time, 0, it's at minus 80. Time 1, it's minus 80. Time 2, it's at minus 50 or 30 or something like that. And then time 3, it's at plus 20 all of a sudden, right? It went from a very negative to all of a sudden a positive charge. And then they kept on monitoring, and then they say, oh, look, it's going down again. They looked at it at time 5, and they said, oh, it's 0 volts again or something, right? And then they found like this, right? So they can measure it and see what the voltage change over this course of time right here. Right? So the y-axis is the millivoltage. Over here, and the x-axis is time, right? Most of the graphs you look at, the x-axis is time, right? Over here, you're just measuring thing according to time. So in this one, though, they're not measuring millivoltage. On the bottom over here, they're looking at the amount of tension that's generated in corresponding with these voltage changes, right? And they could see that there was this period of time where there was no tension generated, time 1 and time 2, and that time 2 would correspond with, say, this big spike in the membrane potential change, right? And then they'll see time 3, all of a sudden, oh, it's starting to raise over here, right? The muscles are starting to generate some tension at time 3. Time 4, it's generated tension. What's going to happen? Is it going to generate more? No. At time 5, it's starting to go down again, right? Less tension generated. So here they're measuring tension, right? How hard something is pulling on something. So that's the y-axis on this case over time in relation to this. Any questions on reading a graph like this, what we're talking about here? And again, for these three, the x-axis is time changing as we move along here, right? And then they're monitoring the voltage change or tension generated. And we'll talk about these muscle twitches in next lecture or so. But right now, I just want you to understand how a graph works. We're going to measure tension, and how we're going to do that. In this case, when they study these things about muscle length and tension generated and stimulation, right? In this case, it's an artificial setup where would be the nerve fiber going into it, sending off an electric signal. Right? In this case, it's going to do it in some other way, right? But that it's going to release, it's going to cause this muscle to twitch in some way through this electric signal. And when it does so, the muscle is going to contract, right? And it's going to create a little pulling force on this right over here. It's going to create tension, and that's going to be measured. In this case, of course, now it's all electronic, but in this case, it's going to kind of give a reading immediately of how much tension is generated when you stimulate this muscle right here, right? It's going to create a pulling force on the weight that it's attached to right here. And usually they do these what's so-called isometric, that is, they don't let the muscle actually pull anything. They just see the tension generated as it doesn't change. So what this graph is showing, right, as you either stretch the muscle and then put a charge in there right there, they measure the active tension, and then they plot it on a basis not overall length of the muscle, but they somehow deduce the length of the sarcomere, right, as the tension is generated, right? The length of this will correspond to the length of the muscle, and they'll see that at this level, right over here, there's a certain amount of tension generated, and as the sarcomere length increases from this, or as the muscle length starts getting stretched out a little bit, it's actually able to generate more tension. And that's going to keep on working over here until it reaches a certain length. And then that's going to kind of flatten out over here. And they're all doing it on this sort of measurement scale right there, right? So in this case, it's not time that they're measuring, but rather they're measuring the muscle length, right? And here they're kind of measuring the sarcomere length in some way. I don't know how they're actually measuring the individual sarcomere length. They'll probably deduce it based on the length of muscle. That's not important. But we can see that as the sarcomere length increases, we're able to generate more tension. This is a lot of words right over here, but the bottom line is the cross bridges are only going to be able to form, right? The cross bridges, the myosin heads and the actin filament are only going to be able to form where there's an overlap, right? So the starting length of the sarcomere is going to reflect that overlap, and it's going to have an influence on the ability to generate a particular force as that sarcomere shortens, right? So at different lengths, they're going to generate a different force, right? Or said differently, they do not produce the same amount of force when they're activated at different lengths. Right? So when a skeletal muscle fiber contracts, the myosin heads are going to attach the actin to form cross bridges, followed by the thin filaments sliding toward the thick filaments, right? That is what creates the tension ultimately of the muscle contraction, right? This is what's creating the tension. And then we have an ideal length to produce maximal tension, which is going to be about 80 to 120% of its resting length, right? When the muscle is relaxed. And the definition of maximal tension is this 100%, where the medial edge of the thin filaments, that is the medial edges of the thin filaments right over here, are just at the most medial myosin heads of the thick filaments, right? Remember, you got that tail end over here, and then this is the most medial myosin heads over here. This is where you're going to be able to generate, this is where you maximize the overlap between the actin binding sites and myosin head, right? Because there's going to be the greatest overlap. This is where you're going to be able to generate most tension. If you start contracting, there's a point, right, where you're going to start to beyond 80%, where the zone of overlap is actually going to be reduced, right? Where the formation of cross bridges is not possible because they're not in contact anymore. That's going to reduce the ability. You can't generate as much tension as you were here. Vice versa, when you're stretching your muscle, right, past your resting length over here, there's going to be a point where you have less and less interaction over here until there's actually a point theoretically where you could have no interaction at all. And then of course you couldn't generate any force. This is usually not anything that happens due to like the tighten in here. That won't allow that, right? Your tighten prevents this from overstretching. All right, so you don't want it too short. You don't want it too long, right? You want this perfect overlap here. So now we just get to this graph, right? Reading this graph, and that's all what this is about right here, right? In this case, we have on the y-axis here, the tension developed, and they're just putting it as a percent of maximum. Here's the most tension you could possibly develop. And then these are the less 80% of that, 60% of that. And then on this side, you got a percent of your optimal length. That is where you can generate the most tension. And then on either side of it is slightly less than optimal. Okay, so we'll see at when the muscle is very contracted, when you're contracted, totally contracted phase, 60% of its resting length, you generate zero tension. And then if you were something like, I don't know, whatever this is, 70% over here, you would get 40% of the tension, right? So it's rising from 0 to 40 as your sarcomere length gets closer to 100%. Then when you're around 80% over here of the optimal resting length, right? Still a little slightly one, you're at 80%. Past that point, you rapidly move up toward 100%, right? At that optimal length where there's maximum overlap over here. Right, so in between this range right here is where you can generate the most contractile strength. Right? And then as you stretch it out more, right, 120%, you start to get down back to which is about the same of, this length over here, and then you rapidly decrease back down to zero efficiency once you get past that zone over there. All right, so that's the length tension relationship. And basically it means like decreases in muscle force generation and lengths different on either side from optimal, a result of decreases in cross bridge formation. Answer to a test right there. Okay, that's what you want to look at.